In March 2026, Nvidia did something strange. The company that sells the most important chips in the AI boom did not buy a model lab. It did not acquire a cloud platform. It did not invest in another GPU manufacturer. It committed $4 billion to two laser companies, two manufacturers most investors had barely thought about, two companies that do not build AI models and do not make the chips that made Nvidia the most valuable company on Earth. That investment is the tell. To understand what it signals, you have to understand one thing about how AI clusters actually work. A Blackwell accelerator costs $30,000 to $40,000, but inside a 100,000 chip cluster, that GPU is only valuable if it stays busy, fed a constant flow of data from other chips, other servers, other buildings. When that flow slows, the GPU does not get cheaper, it just waits. And a waiting GPU is the most expensive object in the world. The network is what keeps it busy, and right now, the network cannot be built fast enough. The AI boom has a pattern. Infrastructure bottlenecks do not disappear, they move. In 2024, it was GPUs. In 2025, it was memory. In 2026, the constraint has shifted to the hardware connecting every chip to everything around it, the networking layer. The most acute bottleneck sits inside the optical transceiver, the device that converts electrical signals to light so data can travel between racks at the speed AI requires. And inside that transceiver, a laser built on a specialist material that only a handful of companies in the world can produce at scale. Right now, production cannot keep pace with demand. The shortage that began this year will not be resolved by the end of it. To understand what that means, we will look at three things. First, why networking has become existential to AI infrastructure and why the physics of large-scale GPU clusters made this outcome inevitable. Second, what is actually constraining the networking build-out, where the shortages are, and what makes this crisis harder to resolve than the GPU and memory shortages that came before. And finally, which companies are positioned in front of the shift, and why Nvidia's $4 billion bet on lasers signals something larger than a supply chain hedge. Let's unpack this. A GPU has one job. It does not retrieve data, it does not store data, it does not decide what to compute next. It takes in data, performs an enormous amount of mathematics on it at high speed, and produces an output. Its entire value is contingent on a continuous flow of data arriving at the rate it can process. Remove that flow, and a $40,000 chip becomes an expensive heater. For most of computing history, this was not a serious problem. A single GPU or a small cluster of them could be fed from local memory fast enough to stay busy. The network was background infrastructure, important, but not the thing that determined whether the system worked. That changed when the clusters got big. The AI clusters being built today are not server rooms, they are campuses. Microsoft's latest Nvidia deployment connected 4,688 GPUs into a single supercomputer-scale system. The Stargate project, the joint venture between OpenAI, Microsoft, and SoftBank, is building toward clusters in the hundreds of thousands of chips spread across multiple buildings, drawing more power than a mid-sized city. At that scale, networking, the full layer of hardware connecting every chip, every server, and every building, becomes the defining infrastructure challenge. Every server in a 100,000 GPU cluster needs high-speed connections to everything around it at 800 gigabits per second across racks, rows, and buildings. At those speeds and distances, data travels not through wire, but as pulses of light through optical fiber, and at every junction between fiber and server, a small device converts between the electrical world of the chip and the optical world of the cable. In a 100,000 GPU cluster, there are millions of those junctions. Industry estimates suggest that for every dollar spent on AI accelerators, hyperscalers spend an additional 40 to 60 cents on networking hardware. Apply that ratio to more than $450 billion in AI infrastructure spending in 2026, and networking hardware becomes the second largest line item in the most capital-intensive build-out in the history of technology. And yet, the networking hardware required to build these clusters cannot be manufactured fast enough to meet demand. By the way, if you want to track where AI infrastructure spending is actually going and which companies are sitting in front of that demand, that is exactly what we cover every week in our newsletter, ARPU. If you want that kind of analysis in your inbox, subscribe at the link in the description. The networking stack is not a single technology. It is a hierarchy of layers, each with a different function, a different supply chain, and a different set of companies inside it. Start at the bottom, the physical layer, where the constraint is most acute. Each optical transceiver depends on a specific laser to generate the pulses of light that carry data between racks. That laser, an electro-absorption modulated laser built on indium phosphide, is manufactured at scale by fewer than a handful of companies globally. According to McKinsey, production is running 40 to 60% below demand. New capacity takes 18 to 24 months to build. Geography deepens the problem. China controls 70% of global optical transceiver production and dominates upstream indium supply. In February 2025, China placed indium phosphide on its export control list. In a period of escalating trade restrictions, that concentration transforms a capacity problem into a supply chain risk. The companies that own this layer are Coherent and Lumentum, the two largest Western manufacturers of optical transceivers and EML lasers inside them. Both received Nvidia's $2 billion investments in March 2026. InnoLight, the Chinese manufacturer, is the counterweight, 20% global market share, and a cost structure Western peers struggle to match. Corning sits slightly apart, manufacturing the specialty optical fiber that carries light between buildings and campuses. Fiber demand grows with every new cluster built, regardless of what happens at the component level above it. It is the quietest beneficiary in the physical layer. The longer-term risk to these companies is co-packaged optics. Today, transceivers plug into switches as separate, replaceable modules, the standard approach for the past 2 decades. CPO replaces that by integrating the optical engine directly into the switch package itself, placing the photonics millimeters from the switch chip rather than at the port edge. The result is dramatically lower power consumption and higher bandwidth density. By 2030, CPO is projected to reach 35% of optical ports. That is not a replacement of the pluggable transceiver market, but it is a shift in where optical value sits, gravitating from the discrete module toward the switch silicon designer who owns the integrated package. Move up to the silicon and systems layer, and the question changes. At the physical layer, the problem is who can make enough light? At the silicon and systems layer, the problem is who controls the traffic? Every AI cluster needs switches, the boxes that decide how data moves between servers and racks. But the companies competing here do not all sell the same thing. One sells the chip inside the switch, one sells the complete switch to hyperscalers, and one is betting that the next wave of AI buyers will want a more integrated, enterprise-ready system. That is the split between Broadcom, Arista, and Cisco. Broadcom is the merchant silicon player. It designs the Tomahawk switch ASICs, the chips inside the majority of AI data center switches globally. It sells silicon to OEMs like Arista and white box manufacturers, not finished switches. Its Tomahawk 6 is the world's highest bandwidth switch chip in production. It also co-designs custom AI accelerators for Google, Meta, and Microsoft, a second revenue stream that compounds with every hyperscaler chip cycle. Arista is the hyperscaler systems player. It builds and sells complete Ethernet switches to hyperscalers, running Broadcom's silicon under its own EOS software platform. EOS is the real moat, so deeply embedded in hyperscaler infrastructure that replacing it is operationally painful. Its risk is Nvidia, closing the gap fast in greenfield deployments where buyers have no legacy infrastructure to protect. Cisco is the enterprise and second wave AI player. It targets enterprises, sovereign clouds, and neoclouds that lack the engineering depth to assemble best of breed components themselves. Its Silicon One ASIC powers its own switch line, backed by decades of enterprise relationships. If the AI build-out extends beyond the hyperscalers, Cisco is positioned for that second wave. At the top sits the platform layer, and one company not competing within a single layer at all. It's trying to own them all simultaneously. Nvidia's networking revenue hit $14.8 billion last quarter, up 199% year over year, exceeding Arista's entire annual revenue in a single quarter. NVLink is its proprietary rack-scale interconnect, connecting GPUs at 1.8 terabytes per second per chip, 18 times the bandwidth of any external network. InfiniBand is its high-performance networking protocol, purpose-built for large-scale AI training, and remains the dominant interconnect for the largest clusters in the world. Spectrum X is its newer Ethernet platform, engineered to deliver near InfiniBand performance on open infrastructure. And through its investments in Coherent and Lumentum and its CPO switch program, Nvidia is now entering the physical layer too. No other company in the stack is executing across compute, fabric, systems, and optics simultaneously. That's what makes the networking constraint different from the GPU shortage of 2024. The GPU shortage had one logo on it, Nvidia. Secure the allocation, and the problem had a center of gravity. Networking has no equivalent gatekeeper. The optical constraint sits with laser manufacturers, partly in China, on a material with a multi-year scaling curve. The silicon constraint sits in shared foundry capacity that every major technology company is competing to access. No single company controls both. No single investment resolves them together. The first phase of the AI boom was a race to secure the chip that computes. The next phase is a race to secure everything required to connect them. So, where does that leave us? AI infrastructure is entering a more physical phase. The bottleneck is no longer only how many GPUs a company can buy, but whether it can connect them fast enough, reliably enough, and at scale. That means the market has to start valuing a different set of assets: lasers, optical modules, fiber and cabling, switch silicon, switch systems, and GPU networking platforms. The companies that control those layers are not necessarily the ones that defined the first phase of the AI boom. They are the ones that may define the next. And that raises the next question. If Nvidia is building a vertically integrated monopoly across every layer of the networking stack, can the Open Standards Coalition move fast enough to stop it? That is exactly what we cover every week in our newsletter, ARPU. The link is at the top of the description. Thanks for watching.